Hi. So let's learn about interaction effects in multiple regression. And I'm going to start with the case of linear times dummy independent variables, and this will become clear as we move along. First of all, usually we work with additive models. So what that means is that we assume that each partial effect in our model is independent of other partial effects in the model. So for example, in this model here, we have two independent variables, x2 and x3, and we are regressing y on these two independent variables. And this regression equation assumes that the effect of x2 on y is the same within each value of x3. So for example, let's suppose that x3 has only three values, 1, 2, and 3. Then we are assuming that the effect of x2 on y would be, for example, this slope when x3 equals 3. It would be the same slope when x3 equals 2, but having a different intercept. And when x equals 1, the effect of x2 on y still has the same slope. But in each of the x groups, the intercepts are different, but the slopes are exactly the same. So the effect of x2 on y is the same regardless of the values of x3. That's an additive model. So the effect of x2 on y, that is beta 2 in this case, is the same across the values of x3. That's an additive model. Now what is a non-additive model? Well, this is when the effect of x2 on y is moderated by the values of x3. So when x3 is 1, in this group here, when x3 is 1, the slope effect of x2 on y is relatively small. But when x3 has the value 3, the slope for the effect of x2 on y is relatively large. So the slope is different for the effect of x2 on y across the values of x3. Well, if that is the case, then this simple model where we have x2 and x3 regressed on y, well, that's a misspecified model because beta 2 is not the same across the values of x3. That would be a misspecified model. We are failing to account for the fact that the effect of x2 on y is different across the x3 values. So we would denote an additive model like this. x2 and x3 impact y. They have partial effects on y. But we denote a non-additive interaction effect like this. So the effect of x2 on y is moderated by x3. Alright, so we've already actually worked with non-additive models before. This is when we looked at nonlinear effects. So when we took x and multiplied it by itself and created x in the power of 2. And in this model here, we had x and x2 in the model to represent a curvilinear effect. Well, this is also a non-additive model because the model argues that the effect of x on y is moderated by the value of x. So the effect of x on y, that is beta 2, is moderated by the value of x. Either it's moderated by x in this way, like a ball shape, or it's moderated by x in this way, in a U shape. So when we have interaction effects where one variable is moderated by another, we must create multiplicative terms, just like we did when we created curvilinear effects, but here we're multiplying different variables together. Okay, so we're going to be estimating this equation here. We have y we have x2, we have x3, and we're going to assume and test whether x2 and x3 interact. And to do so, we need to multiply x2 and x3 together, create a new variable, a multiplicative interaction term. This is what this is called. And for this interaction term, it'll be just another variable in our model. We are going to have a specific coefficient, beta 4, and beta 4 is going to tell us about the interaction effect. So this equation argues that beta 2 is moderated by the value of x3, and also that beta 3 is moderated by the values of x2. And beta 4, the coefficient here for the interaction term, tells us if there is interaction. And the significance test for beta 4 will tell us if the statistical interaction is significantly significant. So let's use this example. And usually when we get an example here, as always, things become clearer conceptually. So for example, let's work with 3 variables here. So I'm going to be working with a variable prestige, or occupational prestige. These are scores from 1 to 100. Education in years, or educ, and the variable female, which is a dummy variable for gender, where 0 is male and 1 is female, so traditional gender. We suspect that the effect of education on prestige, we are of course assuming that, you know, more education brings more prestige, occupational prestige. But this effect of education on prestige might differ between the genders. So the effect for male and female might be different. It might be moderated by gender. So maybe education brings, has more advantage for males. Maybe education has more advantage for females. We are going to check. So we're going to use this specification to test. I have education, and this is supposed to be predicted value of prestige. So we have predicted prestige, we have an intercept, we have the education variable, we have the variable for female, the dummy variable for gender, and then we have education times female. This is the interaction term. What we're going to be seeing here is that if beta 4, the coefficient for the multiplicative interaction term, if the beta 4 is significant, then we can conclude that there is a significant interaction effect, that the effect of educ on prestige is significantly moderated by gender. How so? Well, if I'm male, then the equation becomes y equals to beta 1 plus beta 2 educ plus beta 3 times 0, because if I'm male, I'll get a 0 on the variable female, plus beta 4 educ times 0, because if I'm male, I will get 0 on the variable female. And this leaves me with an equation for males, which will be simply beta 1 plus beta 2. So if I back up this part of the equation here, just these two, beta 1 and beta 2, this will be the equation for males. What if I'm female? Well, if I'm female, I can plug in 1 for female and 1 for female here. This is the variable female, this is the interaction term. I get 1 here on the interaction term, and this leaves me with beta 1, beta 2 educ plus beta 3 plus beta 4 educ, because educ times 1 is educ. And this leaves me with an equation for females where the intercept is beta 1 plus beta 3, and the slope for females is beta 2 plus beta 4. So the slope for males is beta 2, the slope for females is beta 2 plus beta 4. So the difference in the slopes between males and females is beta 4. That's the difference in the slope effect for males and females, right? So that's why I'm looking at the significant effect for beta 4. That tells me if the slope effect of education on prestige is different, significantly different between males and females. Alright, so now let's look at some data. I'm going to be using GSS 1998 dataset, this old social survey dataset that I often use in these examples here. And I'm going to just first look at the variables. So analyze descriptive frequencies. So we're going to be looking at the variable prestige, which is called prestige 80 in this dataset. We're going to be looking at the variables EDUC, or education in years, and I'm going to be looking at the variable sex, which is males and females. Let's create syntax for that. So here something unusual happens. So this is, you can see this is sex, one male, 2 female. I need to change that into a dummy variable, 0, 1 variable. Here's education, which runs from 0 to 20, that's okay. But then we have prestige, and we can see it goes up to 86 points. But we also have the value 0, and it's clear here that 0 has to be defined as a missing value, because those who have 0 can be don't know, non-applicable, and so forth. So we need to define these as system missing, actually. In addition to those who have already been defined system missing. So I'm going to do that now. I'm just going to start with that. So recode, pressed, you know, we can run into all sorts of issues when we see actual data. 0 equals to sys miss, like that, and I do like that, and I rerun. I'm just going to rerun the frequencies to see if everything's okay. No, yeah. So I just got rid of the zeros. Now they're defined missing values. So now to be ready to do the equation, I need to do 2 things. I need to change sex into female, a dummy variable for female, where males are 0 and females are 1. And then I need to create the interaction term. So let's first recode sex into female, so recode sex. So those who are 1 on sex will get 0 on the variable female. So males will get 0, 2 equals 1, and females will get 1 on the new variable female, into female, right? So let's see if that works fine for us. Yeah, I have to put that into the window also. So I'm just going to run the frequencies on female also, like that. So here we have the new dummy variables for female, and we can see that all the females are now 1 on this new variable female, and all the males are 0 on the new variable female. So we have a dummy variable. And now we need to create the interaction term. And we do compute, and we're going to create the interaction term EDUC times female. This is the name I'm going to give the variable. And now the function, this variable should be EDUC times female. Please SPSS create a new variable called EDUC times female, and it should be equal to the variable EDUC times the variable female. So I'm running this variable, and now I have created the new variable EDUC times female. I'm just going to put it here and see how it looks. It should be at the bottom. So this is the new variable. it runs from 0 to 20. And it's really meaningless unless it's situated in the equation that we're going to use it in. Okay, so let me just start doing something here. Let's just first look at the effect of education on prestige. First only among males and then only among females, just to see. So if I just start by looking at the effect of education on prestige, like that, I can actually go to selection variable and choose a group. And I'm going to choose female. I'm going to put female here. This is a selection variable, so I can run the regression for a subcategory of cases. And the rule first is the value 0. That's the males. So I'm just gonna look at the effect for males first. And I'm gonna paste that command. And I'm gonna do another regression where the rule is females equals to 1, like that. And so this will give me the effect of education on prestige for females. And I'm just doing this to show you before I actually estimate the interaction equation. So now I have two different equations. I have the same equation, the effect of education on prestige among males and among females. Let's just look at, just to compare. So here we get the equation for, here is the female equals to 0, so this is the equation for males. So the slope for males is 2.1. The effect of education on prestige for males is 2.1, and the intercept is 16. And for females, the effect of education on prestige is 2.6. It's a bit higher, but the intercept is 9.1, or it's actually 9.2. So, and I've actually done this here just to show you. So we can, of course, perform regression for subgroups and see how education influences prestige among males and females separately. And we can see that the slope effect for females is higher than the slope effect for males. So females are getting more prestige out of education than males, but their starting point is lower, right? Because their intercept is 9.2 for females, but 16 for males. But although the slope for females is higher than for males, we do not yet know if the slope effect is significantly different between males and females. Is the difference between 2.6 and 2.1, is that statistically significant or not? Here we need to estimate a non-additive model. So before showing you the results, I'm just going to show you how to do this. So we already created the multiplicative interaction term. So now I'm just going to run a regression linear, and I'm going to throw out the selection variable. But now I am going to put in, as a deep independent variable, I need to put in female, and I need to put in education times female. So I have to have the first order variables and the product term all in the same equation. And we estimate. And now I get findings. So we have an equation, and I can see the slope effects here listed for education, female, and education times female. And I get t-tests and p-values for each of these coefficients. And they're all significant. You can see that here. Now I'm going to go to the PowerPoint. So we have findings. First, we have the first number in this equation will be the intercept for males. I'll show you why this is the case. The slope coefficient for EDUC is significant, but this is the slope only for males, 2.1. We actually saw 2.1 earlier, remember, when we did it for the group separately. This is the intercept change for females. So if this is the intercept for males, 16, this is the change in the intercept for females compared to males. And the difference is statistically significant. Finally, this effect here, this is the interaction effect. It is statistically significant, so there is a statistical significant interaction. And this 0.5 is the change in the slope for females compared to males. So the slope effect is 0.5 higher for males than for females than it is for males. The slope is 0.5 higher for females than it is for males. And that difference is statistically significant. How so? Well, if I'm male, I can plug in 0 for female, and this will become the equation. 16 plus 2.1 education. The intercept for male, prestige when you have no education, and 2.1, for every year increase in education, prestige goes up 2.1 points. If I'm female, we need to plug in 1 where there is female in the equation. So this will be 1, and this will be 1, and that gives us 2.1 education minus 6.9 plus 0.5 education. So I can sum these together, 16 and minus 6.9, and I can sum 2.1 adduc and 0.1 adduc, 2.1 plus 0.5, which is 2.6 adduc, right? And this will be the equation for females. This is the equation for males. This is the equation for females. And we already know that the difference between 2.1 and 2.6 is statistically significant. So there's a significant interaction effect. Education has more effect on prestige among females than it has among males, but the intercept is higher for males, so they start at a higher point, like that. So males start in prestige when they have no education at 9.1. That of course is meaningless at this stage. Well, actually there are people with no education in the data. So females start at 9.1, and their prestige increases by 2.6 for each year of education. So when about 14 years of education is reached, females surpass males in this simple regression. Of course, there are a lot of things that we haven't controlled for. Whereas the intercept for males is 16, and for every year of education, their prestige increases by 2.1. And the difference in the slopes is statistically significant. So there's a statistically significant interaction effect. And this calculation is just to find this number here where the lines intersect. That's not really important, but I just did it to draw the graph here. So in the next video, in this video, what happened is that we are multiplying together a continuous variable, education in years, and a dummy variable, female. In the next video, I'm going to multiply together 2 nominal variables, and then in the final video, I'm going to multiply together 2 continuous variables.